Now in section 7.5, we are going to solve trigonometric equations. So this will be a lot like algebra. Actually, we'll be using algebra most of the time. Occasionally, we will dip into our trigonometric identities just to make it easier for us to solve. And we will definitely need to refer to our unit circle. So let's look at a trigonometric equation. It's an equation that uses a trig function, and see if we can solve it. 2 cosine of x equals negative. I'm solving for x. So I might start by dividing by 2, both sides. 2 divided by 2 is 1, and I'm left with 1 times the cosine of x equals negative 1/2. So now I need to solve for x. I might just take the arc cosine of both sides. Remember, that's our inverse. You're not going to divide by cosine because it's a function. You don't divide by a function. You take its inverse. So the arc cosine of the cosine of x, as we talked about in our last video, is x. Just like the square root of something squared is that something. And so now we're looking for the arc cosine of negative 1/2. Where does the cosine equal negative 1/2? Let's go back to our unit skittle. I know it's a unit circle, but I can't draw a good circle freehand. So cosine values are my x values. It crosses at 2 locations. Here in the second and third quadrants. I could go to my calculator and type in arc cosine of negative 1/2. I know that arc cosine works in the first and second quadrants, and so it would give me an answer there. What if I've forgotten my calculator? Well, I can still do this one by hand. I happen to know that with a 30, 60, 90 triangle, the ratio of sides is 1 to √3. And I went to this one because we had 1/2 as our input to the arc cosine. And I remembered that ratio of sides from that triangle. So the angle whose cosine is 1/2 would be 60 degrees. Now this is negative, so our reference angle is 60 degrees. So for this angle in the second quadrant, if the reference angle is 60 degrees, the original angle is 120 degrees. In the third quadrant, we would add 60 to 180 and get 240. Now, as we also said in our last video, because we don't have a limitation on here, we have to consider all of the coterminal angles. So anything times 360 degrees added to what we originally have will give me a coterminal angle with those that I've been given. Again, the calculator, arc cosine of negative 1/2, will give me 120 degrees. It won't give me the 240, so I had to know that there were 2 spots on the unit circle that had a cosine of negative. And I had to also be able to extend that to all coterminal angles. So that would be my full entire result. Let's look at another problem. Lots of times they will say in 0 to 2 pi. And if they do that, then you know it's within 1 revolution. We don't have to add the k plus, in this case, it would be 2 pi instead of 360 because they asked for radians. But our result would just be within that 1 revolution. So we would have been able to say just 2 pi over 3 or 4 pi over 3. All right, let's look at another example. Funny, I added a layer, wrote on that one, and would have kept the first one. All right, how about 4 sine squared x equals 1? Well, let's go ahead and divide by 4. Seems like something we would do algebraically. because 4 divided by 4 is 1. And now I've got sine squared x equals 1/4. Let's take the inverse of the square. So we'll take the square root of both sides. And the sine of x would equal plus or minus 1/2. So where is the sine of x equal to plus or minus 1/2? Sine are the y values. So -1 or positive 1/2 would be there. -1/2 would be there. Those cross my unit circle at 4 places. So I've got 4 angles to look at. Now again, I could use arcsine in my calculator. Arcsine works in the first and fourth quadrants. The answer it would give me is 30 degrees. And that's true for that one spot. I have to know that this goes beyond that, and I have actually 4 reference angles. I wrote 40 because I said 4, that's what it is. All right, so my answer would be the 30 degrees, or pi over 6. It would be 150 degrees, which is 5 pi over 6. It would be 210 degrees, which is 7 pi over 6. Or it would be 330 degrees, which it would be 11 pi over 6. So those are all of the answers within one revolution. If we wanted to include all coterminal angles, we would take each of these and add, well, you know, maybe I don't have to add 360 to all 4 of them. Because 30 plus 180 is the 330. Those two kind of, I'm sorry, 30 plus 180 is the 210, 150 plus the 180 is 330. So maybe I just take the 30 and I add k times 180 degrees. That would pick up the 210 and then any coterminal angle with both of those. I could add k times 180 to the 150, and that would grab the 330 plus any coterminal angle of those. So because those are exactly 180 from each other, just adding 180 or adding pi, depending on if you're in degrees or radians, will pick up both of those and toggle back and forth as you work your way around the circle many times. So sometimes we don't actually have to add the full 360 to all 4 angles. We can just use what we have and add maybe a 180. So think about that. We have to actually think beyond what our calculator tells us and a little beyond just the basic, quick default answers. Well, let's look at one that's even a little weirder. Let's take maybe 3 times the tangent of 2x equals -3 on the interval from 0 to 2 pi. See, if they put an interval on it like that, now I know it's 1 revolution because 2 pi is 1 revolution around the unit circle. I also know my answer needs to be in radians because the interval they gave me was in radians. So that limits what I'm looking at a bit here. Let's go ahead and divide both sides by 3. Again, we're trying to isolate our variable here. 3 divided by 3 is 1, so I've got the tangent of 2x equals -1. Well, I'm going to take a quick look at, I draw my skittle first. You know, it's funny, I'm better on the whiteboard, but need to get better at this. All right, so where is the tangent equal to -1? All students throw chalk, meaning all functions are positive in the first quadrant, sine is positive in the second, tangent is positive in the third, cosine's positive in the fourth. Tangent would be -1 here and here, with a reference angle of 45 degrees or pi/4. Okay, so this would be 3 pi/4, and this would be 7 pi/4. Those two angles have a tangent of x being -1. Now we have the tangent of 2x. So what we're saying, x is between 0 and 2 pi. So 2x has to be between 0 and 4 pi. Notice what I'm doing now is just changing perspective on that angle, because we're looking at 2x is the angle whose tangent is -1. Later, we'll kind of bring it back to x. So where within 0 and 4 pi do we get a tangent of -1? So 2x would equal 3 pi/4, 7 pi/4. Now we have to go around the circle one more time. So we're going to add another 3 pi/4 to that, or I'm sorry, add another pi to it. So 11 pi/4, and add another pi to that, and we get 15 pi/4. So all of those would equal 2x. Well, I just need x. To get x, I multiply both sides by 1/2 or divide by 2. And all of this is because the angle that they told us, tangent of a big angle, is -1, and we need the smaller angle. So we had to change our perspective a little. If I have each of these, remember you multiply numerators together and denominators together. So my answer for x would be 3 pi/8, 7 pi/8, 11 pi/8, and 15 pi/8. If I plug any of those into this function, I'll get a true statement. So let's plug in 3 pi/8. Tangent of 2 times 3 pi/8 does that equal -1? Well, 2 times 3 pi/8 is 3 pi/4, and tangent of 3 pi/4 is indeed -1. We can check all of those and they'll work out just fine. And it was perspective that gave it to us. We knew that the tangent of 2x was -1. That was between, well, x had to be between 0 and 2 pi. So 2x must have been between 0 and 4 pi. We found all of the angles between 0 and 4 pi whose tangent was -1. And then we halved each of those to get the actual x value itself. Like I said, it's a pretty weird one, but it works pretty well. All right, let's do another one. Again, keep in mind, we're kind of talking algebra here. So if I've got 2 cosine squared x equals 1 minus cosine x in 0 to 360, so I know I'm in 1 revolution. I know they want the answer in degrees. Now I need to solve for x. Well, algebraically, I really like getting both things on one side of the equal sign and having it equal 0. Because then I might be able to take advantage of the 0 factor property. So I've got 2 cosine squared x plus cosine of x minus 1 equals 0. That looks an awful lot like a quadratic. I mean, if it looked like 2t squared plus t minus 1 equals 0, you would say, oh, yeah, that's quadratic. It's a parabola that opens up, and well, how would we solve for this? Well, maybe we'd factor it. We would say 2t times t equals 2t squared. 1 times 1 is 1. And now, because it's negative 1 over here, one of these factors has to be negative, the other positive. Well, I know I want the outside plus inside to equal plus t. So here I've got 2t and t. If I had a positive 2t and a negative t, that would equal t when I add them together. And now we could set each of these equal to 0 and solve for t. Well, let's do the same thing over here. Let's go ahead and factor this. I know that 2 cosine x times cosine x is 2 cosine x, cosine squared x. 1 is just 1 times 1. Again, outside inside has to equal to the middle term. So if I had a positive 2 cosine x minus 1 cosine x, I'd get a positive cosine x. Set each one equal to 0. Taking advantage of the zero factor property. And I've got cosine x equals -1, and I've got cosine of x equals 1/2. All right, let's go to our unit circle, or skittle, such as you draw. Where is the cosine equal to -1? Well, once again, cosine are the x values, and that equals -1 right here at 180 degrees. Where does cosine equal 1/2? It's over here at 2 places, at 60 degrees, and at, with a reference angle of 60 degrees, 300. So x would equal 60 degrees and 300 degrees. So my answer to my original function was x equals 60 degrees, 180 degrees, and 300 degrees. If I plugged in any one of those three into my original equation, I would get a true statement. And so notice it was almost strictly algebra. I did this other one in maroon to show you that it looks exactly the same. I just replaced cosine x with t, and then it was familiar and comfortable to many of you. Having cosine x in there isn't any different. I had to write more. That's the only difference. But I can treat it the same. I can factor just like I did before, and I can get a good result. All right. What if we've got some combinations of functions? Notice I'm just solving a bunch of problems at this point because the concept is what we've covered algebraically for years. What if we have sine of x plus cosine x equals 1 in the range of 0 to 2 pi? So I'm using radians as my result, and I'm within 1 revolution. This looks a little different. What can I do? You know, those two on the left side were squared. We'd have an identity. Let's see what we can do. Let's square both sides. Now remember that squaring a binomial does not just give you the square of the two terms. If you wrote it out twice and FOILed it, you'd see there's this inner term that's twice the product of the two terms in the binomial. And then we have those other two squared, and 1 times 1 is 1. All right, I'm going to rearrange this just a little bit to make it look a little more comfortable to me. So I've got, because of the commutative property of addition, I can just move things around and it will equal the same thing because these are all added together. Well, the reason I did that was what started this whole thing off. That identity, sine squared plus cosine squared, is 1. So now I have 1 plus 2 sine x cosine x equals 1. If I subtract 1 from both sides, I have 2 sine x cosine x equals 0. So I have factors on one side set equal to 0. That's prime for taking advantage of the 0 factor property. I could divide both sides by 2 and we could see that that 2 becomes irrelevant, really. But set all of my factors equal to 0. Back to my unit skittle here. Sine are the y values. Where does y equal 0? That's the x-axis. That's in 2 places, 0 and pi. And whereas cosine equal to 0, cosine are the y values. That happens at pi halves and 3 pi halves. So for this equation, I could plug in any one of those 4. Let's double check with our original function though and make sure that that works. So our original function was sine of x plus cosine of x equals 1. All right, let's plug in those 4 angles, 0, pi halves, pi, and 3 pi halves, and see what we get. So we've got sine of 0 plus cosine 0 equals 1. Sine of pi halves plus cosine of pi halves equals 1. We've got sine of pi plus cosine of pi equals 1. And we've got sine of 3 pi halves plus cosine of 3 pi halves equals 1. And let's see what we get. Well, we know that the sine of 0 is 0. The cosine of 0 is 1. 0 plus 1 is indeed 1, so that checks. Sine of pi halves is 1. Cosine of pi halves is 0. 1 plus 0 is 1. That checks. Sine of pi is 0. Cosine of pi is negative 1. 0 plus negative 1 is not 1, so that does not check. Sine of 3 pi over 2 is negative 1. Cosine of 3 pi over 2 is 0. Negative 1 plus 0 is not 1, so that doesn't check. Our result is therefore just 0 and pi halves, because that is the only 2 angles that we can plug in here and get it entirely right. We saw that in algebra. There were times where we got an answer to a quadratic equation that worked great for that portion, but it didn't work back in our original function. So sometimes you'll need to plug these back in and check, make sure that they really work. If they do, you're golden. If they don't, just discard it. You followed the rules of math, you will get answers, and some of those answers will carry forward and some will not. Go ahead and play with this a bit. You may have to grab a couple of identities like we did here, but you'll be able to solve trigonometric equations just fine. But if you have questions, let me know.